Basic atomic particles. A. Electron. Expert discovery of electron. The discovery of the electron was initiated by the experiments that were carried out by 1. Crookes in 1875. By using a tube, the cathode rays produce flowing rays. From negative pole to pole, positive indicates that negatively charged rays. Further investigation show that the rays the cathode is particle, the smallest and the lightest. 2. J.J. Thomson. This research was continued by Thomson. By substituting cathode with another metal, the result was the same. Thomson concluded the cathode rays is negative particle contained in all atoms or colored electrons with the symbols 0e mean 1. Its mass is very small, that is 9.11 x 10^28 grams, so consider it uncharged. B. Proton. Expert discovery of electrons. The discovery of the electron was initiated by the experiment were carried out by Goldenstein in 1886. Proton discovered by Golden in 1886 with the using a tube like two corks. The cathode is made hollow. Tube filled with the hydrogen gas produced the canal, raised canal through hole channel at the cathode. The sign is deflective, negative electrified. It was concluded that red rays, those positively charged one, called a proton with a charge of charged electron but the sign in opposite. Symbol 1p1. C. Neutron. Neutron discovered by James Chadwick in 1932 was experimenting with the fire, a beryllium core with the alpha rays. It turns out produce particles without charge or mass neutral equal to 1 H atom. The symbol on 0 in 1. Since the discovery of the neutron, it is believed the atoms are composed of the atomic nucleus, contains proton and neutron, while around there are electrons that are revolved around it. Between one atom and one atom another are divisible by the number of these particles and not the kind. Every atom neutral has a nuclear charge equal to the charge of the electron. In general, the symbol of the atom written as XGA, where A describes the number of P and the number of N. G equals number of P equals number P, and N equals A to G equals number of neutron.
Development of atomic theory. A. Dalton atomic theory. According to Dalton, atom is the smallest part of a material that cannot be further defined. But it turns out that this opinion is not true because of the discovery of electron-based particles, protons, and neutrons. B. Thomson atomic theory. According to Thomson, the shape of the atom jellyfish line up of positive electric charge and negative. Positive charge spread evenly inside the sphere, which is the atom, and the electrons are ordained. Thomson formulated a theory, namely an atom is a small charged ball. Positive and all the surface charged electrons are negatively charged. This model also called the Rosines-Briggs model because It is merely two that breeds sprinkled with raisins. The theory has a weakness that is not explained the position electrons. Thus, saying that the electrons are located and the surface as it was pulled by its positive charge. C. Ernest Rutherford atomic theory. Research conducted by Rutherford, Geiger, and Marsden at the beginning of the century, the 20,000, give a lot information about the arrangements of atoms consisting of negative particles and the positive. Rutherford did experiment with fires and a beam at the platinum plate. Yard observations show that the rays are transparent, bend and bounce. Penetrated because atom contains space hollows. The beam bends because at the center of the atom there is a unit positively charged particle, so that the beam bends when approaching the core because reverse. Rays bounce because it hit the core but so little. Outside the core is not just empty, but there are electrons spinning around the nucleus. Electron does not affect a ray because it's small and light. From these experiments, Rutherford concludes that an atom consists of a nucleus positively charged. One is the center of the mass. Around the nucleus are electrons that surround the inner core vacuum. But Rutherford's atomic model decreases difficulties because it contradicts with electrodynamic theory electricity. According to this theory, electrically charged particle, when accelerated, it will radiate energy. Electrons are moving around the core will be loss of energy continuously due to radiation, so that it will eventually fall to the radiated core. It can be explained by Rutherford. This difficulty can be overcome by Bohr, who applied quantum theory on the atomic model. D.
Bohr atomic theory. This atomic theory starts from Rutherford's atomic model and plays quantum theory. Bohr formulated the atomic theory called Bohr atomic theory, which is as follows. 1. Atom consists of positively charged nucleus. 2. Electrons move around the nucleus in a certain path. 3. The electrons in the path don't absorb or emit energy because each part has a certain energy level. 4. If the electrons move paths, there is a change in energy by delta E equal E2 minus E1. E2 and E1 the energy of the path at low and high levels. Atomic theory can clearly explain the emission and absorption spectral lines of hydrogen atoms. Light will be absorbed or emitted at the specific frequency as a result of the transfer electron from one orbit to another. An atom that is in the stable state has the lowest energy, called the ground level. The ionization energy calculated by Bohr atomic theory corresponds to the third ionization energy, so it can be concluded that Bohr atomic theory only applies to one electron atom, for example lithium. The idea of electrons orbiting the nucleus in certain orbits like the moon orbiting the sun was so easy to understand that Bohr's atomic theory was accepted. However, over time it was realized that this theory could not explain much. When atoms are placed in a magnetic field, one finds a more complex emission field. This event, called the Zeeman effect, cannot be explained by Bohr theory. Sommerfeld, a German physicist, suggested that apart from circular orbits, that are also elliptical orbits. Although the Bohr-Sommerfeld theory could explain the Zeeman effect, it was unable to explain the spectrum of many electrons atoms. Finally, after the 1920 following grouply ideas about the electrons, Webb, Schrödinger, and Heisenberg succeeded in laying the foundation for the modern atomic theory. E. Atomic theory of wave mechanics.
This theory was preceded by the Bernoulli hypothesis that matter electrons is a wave and a particle. The nature of wave becomes more visible if the size of the wavy path means that the electrons have varying distance from the nucleus and not on a fixed path. This opinion was confirmed by Einstein and Planck. According to Einstein, mass can be compared to energy, E equals mc squared, where m mass of matter and c speed of light. According to Planck, light energy depends only on its frequency, E equals hv, where the wavelength of light is equal to the Planck constant divided by the momentum. Based on this, the Bernoulli hypothesis that this equation applies to any matter in motion. This means that an object with mass moving at velocity will form a wave with a wavelength of lambda equals h divided mv. The motion of a large object produces a very small wave. The nature of the wave motion of a large matter is negligible, but for small particles it must be taken into account, such as a neutron. Since then, wave mechanics or quantum foot was born to deal with the motion of small particles. According to the Bernoulli, electrons move in wave rather than in a specific trajectory like Bohr theory. The position of the electrons around the nucleus cannot be determined recently because it is always in motion, which can be determined only by the greatest probability of finding electrons, which are called orbitals. This is in accordance with Heisenberg's principle, namely the principle of uncertainty, according to which a moving particle has a certain position and momentum. Atomic orbitals are obtained theoretically, namely the result of solving the Schrödinger equation.
Hello, in here I will explain about the electron configuration. The arrangement of electrons in the atomic subcell is called the electron configuration. There are three rules used in writing the electron configuration. First, the above principle. Second, Hund setting. Third, Pauli provision. First, the above principle. The above principle states the under basic condition. Electron will occupy electron cell with lower energy, leading to higher energy. The above principle is dependent in the following diagram. You can see in over here. In the figure, it can be seen that the electron configuration using the above principle depends on the addition of the principal quantum number and the azimuth quantum number. The energy order of atomic orbital from lowest to highest is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, and so on. Then the electron will occupy the 1s subcell first and then occupy the 2s subcell. The s subcell can only be occupied by 2 electrons. Next, Hund's rule. If the orbital is valid, then the electrons are in contact with the electrons that have different spin. Suppose that the oxygen atom has 8 electrons. The configuration based on above rules is 1s2, 2s2, 2p4. This means that 2 electrons inhabit the 1 subcell, 2 electrons inhabit the 2s subcell, and 4 electrons inhabit the 2p subcell. According to the Hund rules, the configuration is as follows. Pauli prohibition. As the name suggests, the Pauli prohibition, the exchange of a pair of electrons with the same spin quantum number in one orbital. Suppose an atom has two electrons occupying the 1s orbital, then its electron configuration according to Pauli's provision is shown in figure C.
Atomic properties. Atomic properties are influenced by the number of proton and electron from this atom. These properties, among other, atomic radius, ionization energy, and electron affinity. Atomic radius. Atomic radius is half the distance between two atoms of a kind up in the single. Usually, the distance is measured in picometer and angstroms. Because the electrons are constantly moving, it is very difficult to measure the distance from the atomic nucleus to it. There are several types of atomic radius that are used to express the distance from the atomic nucleus to the outermost stable path of the electron. 1. Including the covalent. 2. Metal radius. 3. Van der Waals radius. Ionization energy. Ionization energy is energy the minimum required to release one electron weakest of an atom or ion. The amount of ionization energy is a measure of the effort required to force an atom to release its electron or how an electron can be tightly bound to an atom. Electron affinity. Electron affinity is energy which is released or that required to entry electrons into atom or ion in the gaseous state.